Okay, welcome back, Regents students, to our second video in the waves unit. This is just I'm gonna talk about some basic features of waves. Hopefully, you have seen the short video that shows waves traveling on a spring caused by a person shaking their hand in different ways. I think it was like 12 seconds. Again, I don't have the equipment here, so we have to rely on YouTube videos to see the phenomena that we're studying. So the first thing I want to point out is that waves are a transfer of vibrations through space, and the transfer is of energy, not matter. If you looked at the videos, if you want to look again, the person shaking their hand and putting a vibration to the spring, the coil of spring that's in that person's hand in that video stays in that person's hand. So when something goes to the other side and hits the other side with that vibration, that coil in that hand stayed here, and what got to the other end was the vibration itself. And the vibration is energy, because if you think about it, I am putting in work. I'm putting a force times distance, and then a force times distance. I put work in to the spring, and then that force times distance, that work gets transferred throughout the spring and hits the other side. And if there were a person there holding the other side of the spring, that spring would vibrate their hand and deliver that force times distance, that work, that energy. So what's moving is not the coil of spring here to the person's. You're not throwing the spring at that person, you're just giving a vibration to that other person. So it's a transfer of energy, not matter. Another example, we'll study sound. Think about this. If I'm talking to a person across a room far away, maybe 20, 30 feet away, they can hear the sound, the vibration of my voice. But if I ate onions for lunch, for example, they wouldn't smell my breath being 30, 40, 50 feet away. So my breath is not, the air coming out of my mouth is not flying across the room into that person's ear. It's the vibration only, okay? And the air kind of stays put. So the first kind of thing I could do to create a wave is just make a single pulse. A wave pulse is a single traveling disturbance instead of continuous vibration. So if I just went like that with the spring, as you saw in the video, I would be sending one pulse going down to the other side, as opposed to shaking my hand continuously and sending multiple pulses. Wave pulses, just a single shake the rope up and down, and then the vibration travels, not the rope again. All right, so the next set of definitions are something that were introduced in the video that you watched before this video. Two main categories of waves: transverse waves and longitudinal waves. And then you could also have waves that are a combination of the two, but we're not going to look into that. More complicated than we need. But a transverse wave, in a transverse wave, the material vibrates perpendicular to the wave's motion. So if I shake a spring up and down and those vibrations move sideways, I have vibrations going up and down, and then the velocity of the energy moving is to the right. That is what we call a transverse wave. Any particular coil anywhere in that spring just momentarily moves up and down. Another example would be a wave at a sports arena. When people rise up and yell and then sit back down, the people are not going around the sports arena. The wave is, right? So they're standing up and down, but the wave is traveling sideways. Transverse wave. There are things that we define, parts of that wave. The tops are called crests in a transverse wave, the peaks of the waves. And that, you probably know that word from ocean waves, when you see, it's the surfers riding the crest of the wave or whatever. So you've probably heard that word. You may not have heard that the bottom of a wave is called a trough. So transverse waves are made of crests and troughs. The amplitude is not the distance from the crest to the trough. So if you're in the ocean on an inner tube and you're going up and down, that total distance you go from top to bottom is not the amplitude. It's the amplitude is the halfway from the location of the water when it's still to the peak or the trough, the crest to the trough. So it's half the whole motion you would go when you went from crest to trough. Another definition is the length of the wave, how far the distance is from a crest to a crest. In physics, we use the fancy Greek letter lambda. Remember the Greek letter, we've already used symbols off the Greek alphabet, primarily for the friction coefficient, mu, right? That's a Greek letter off the Greek alphabet, out of the Greek alphabet. This is another Greek letter out of the Greek alphabet, lambda. Okay, so you see it's like a line that goes up and down inside like that. You don't have to draw it that way if you want. If you wanted to draw a simpler symbol like this, you're welcome to. That works for lambda also. So that's the size of the wave horizontally from crest to crest or from trough to trough. And examples of transverse waves, when you're swinging a jump rope up and down, that's two transverse waves going at the same time. And then light waves, which we'll talk about in a couple lessons away, are also transverse waves. The other kind of wave, transverse is one, the other is a longitudinal wave, which you saw in the video as well. So a longitudinal wave, in a longitudinal wave, the material vibrates parallel to the wave's motion. So they're a little harder to draw. So, like for example, if these are the coils of a spring that I'm holding like that, and I shove my hand forward and backwards, forward and backwards, forward and backwards. So you see my vibrations are going left, right, and then the velocity of those, of that energy, that disturbance travels to the right. So parallel to the wave motion, as opposed to this perpendicular to the wave motion, vibrate like this and go like that. Here you vibrate like that and go forward. Okay, so that is a longitudinal wave. Okay, and so I'm drawing here the coils of the spring. Some places they're squeezed together, in other places they're stretched out. Squeezed together, stretched out, and then those compressions move forward. So the part where the coils are squeezed together, we call that a compression, where the density of the material is larger than normal. And then where the material is stretched out, like maybe the coils are really spread apart, the furthest spread apart, we call that a rarefaction. Okay, an example of a longitudinal wave is sound. Okay, so sound waves, which we'll talk about, I believe, in tomorrow's lesson, are longitudinal waves. Okay, another set of definitions. Phase. Okay, so phase is just like the coordinate or location of different parts of a wave. Okay, so if we start with this point and we were to graph this would be a cosine function, right? Starting at a peak, going to and oscillating like that. If you imagine the x-axis if you plotted a cosine graph, the point where the graph intersects the x-axis would be at a x value of 90 degrees. And then if you go 180 degrees from this starting point along the x-axis, you would get to the bottom of the cosine graph. Go forward 270 degrees, and you hit the axis, and you go forward, you go again to the next peak. You've gone 360 degrees along the x-axis. So those degree values are just called, we call that phase. Okay, so this point is 90 degrees out of phase with the original. That's how we would say what we would say about it compared to the original. You could say this is 360 degrees out of phase, which is really not out of phase. You could just say it's in phase with this because it's the same part of the cosine graph. Last couple things. Waves reflect. like when you look at yourself in a mirror, okay, you see the light waves reflecting. Well, if you were to send a wave on a spring that's connected to something rigid like a wall, so you bolt it to the wall, and I shake my hand up and down and I create this crest coming toward. When it hits the wall, it would reflect, bounce off the wall, and come back as a trough. And so we would say the reflected wave is, from back here, 180 degrees out of phase with the original wave. Okay, so that's reflection with a rigid wall. If instead we had the wave sent on a spring, and the end of the spring was not connected to a rigid wall, but maybe a frictionless ring on a pole that can slide up and down or side to side without any resistance at all. If you sent a crest, it would reflect off that end of the spring and come back a crest. It would not flip over. There would be no phase change. Here, rigid wall, it flips over. Here, non-rigid boundary, it does not flip over, it comes back upright. The video at the end that's attached to this assignment after this video of this lesson shows a class where they created reflection off a rigid end first and then off a loose end, and you will see in that video the waves reflect upside down when it hits the wall, a rigid boundary, and they reflect right side up when they reflect off a non-rigid boundary. So you could watch that video. It's only like a minute or so. The last thing for today is that there's a relationship between wavelength, speed of the wave, wavelength, and frequency. And that is this: the speed of the wave is equal to the wavelength times the frequency of the wave. Okay, so very simple relationship. The problems that you're going to encounter involving the speed of the wave are simply, you're given two of these variables and you're asked to solve for the third one. So for example, maybe I give you the velocity of the wave or speed of the wave, the wavelength, and you have to solve for the frequency. We'll look at more of those kinds of calculations in the next couple assignments for the next couple days when we look at sound and light. This equation is on the reference table, again in the wave section, right here at the top. V equals, well, they say frequency times wavelength, but it's the same formula: wavelength times frequency, frequency times wavelength. Okay, so that's it for the second video lesson in our waves topic, and I'll see you in the next lesson, lesson 3, sound.